Hello everyone, this is Jason Kendall again with another introductory astronomy lecture. Last time we were talking about distances between the Earth and the Sun, and the Earth and the Moon, and the Sun and the Earth, and trying to determine how far away they are and so forth. And we ended up looking at trying to determine the size of the Earth, but yet we really didn't have a good definition for the size of the Earth's orbit around the Sun. And we didn't even get to the point where we described exactly how we know the Earth goes around the Sun. Because for almost 2,000 years, the geocentric model, this geocentric apparent or settled science of the world was geocentrism, meaning it thought that Ptolemy's model of the cosmos, with the Earth at the putative center, with all the planets orbiting around it on deferents, and on deferents had epicycles, and the epicycles were centered on deferents, and the deferents weren't actually at the centered on the Earth, but were centered somewhere halfway between the Earth and something called an equant, and then that was not really the same, and every planet had its own equant, its own deferent, and set of epicycles. Yeah, it's pretty complicated. So the geocentric model of the cosmos is an extremely complicated thing. So what happened then in the latter part of the 16th century? The 16th century saw what we call the Renaissance across Europe. The Renaissance started to actually try to bridge gaps between things. New ideas were flourishing. There was new trade across Europe. And most importantly for us, it was the beginnings of the stepping stones of getting us to what we would call the science of today. So the but it starts in a very strange place. In heliocentrism, the notion that the sun is at the center of the solar system, not just the cosmos, if you will, it's actually the scales start to drop, but they don't really drop until something is really heavily done. So let's actually look at what happened. So Ptolemy's structure of the cosmos persisted well into the 1500s, roughly the 1530s or so, and then came along Nicolaus Copernicus. And Nicolaus Copernicus said to himself, as a mathematician, as a Renaissance man, as a person who wished to actually play around with mathematics and contribute, he wasn't a scientist, he was more of a mathematician, but his science actually I shouldn't say he wasn't a scientist, I should say specifically he was not an astronomical observer. He utilized the data that was embedded in the Almagest in order to make a new model of the solar system and the cosmos. And his model was kind of a heliocentric kludge. Now, typically when you talk about this particular time, you say, oh, the Copernican revolution, this is the time. Copernicus comes along and says, sun at the center, and here we go. This is now the time for revolutions. Well, this is a thing about it, is that when Nicolaus Copernicus came around, he was looking at it mathematically, and he saw Ptolemy's model, and he saw that there were the deferents, and he saw there were epicycles on deferents, and then he saw these equants. And the equants, there was these three pieces to the models, and everything was perfect circles. So you had perfect circle deferent, a perfect circle epicycle, and then everything was off-centered from the Earth by in the direction of the equant halfway between. So this equant really bothered Copernicus. So he said, I'm going to redo all the mathematics such that the sun is at the center. I can eliminate the equants from my mathematics and see what I get. Well, what he got was the sun at the center of the entire cosmos, but kind of. So the sun at the center meant the following, is that every planet orbited the sun, but as they orbited the sun, they had to, but the centers of their orbit weren't the center of the sun. They were the center of the Earth's orbit around the sun. You see how that works? That's kind of weird. Let's do that again. So it wasn't the center of the sun. They weren't centered on the sun. All the planets' orbits outside of, like specifically Mars, Jupiter, Saturn, those were specifically centered on the sun. They were all centered on the Earth's center orbit, with the sun offset from that center. So it's a little confusing sounding, but wait a second, did he make it perfect? Well, here's the thing. There still were the deferents. The deferents were basically around the center of the Earth's orbit around the sun. And then but every planet still wandered on epicycles on top of these deferents. In fact, if you look at the mathematics, they were much more complicated than Ptolemy's. So a lot of people, when Copernicus published his data, it was like, wow, this is a great idea, but it doesn't do anything for us. It doesn't actually help. In fact, it doesn't simplify. There was no great simplification from the idea of the geocentric orbit to the sun-centered orbit. However, one of the driving reasons for Copernicus's action was that he was a humanist, and humanist felt, which felt differently than the medieval Christian thought of the surrounding era. And it was the sense that as humanity was learning more and more things and becoming greater and greater masters of the environment and greater and greater masters of what they could possibly do, that they were becoming more like God. And since he was a minister as well, he was a clergyman, Copernicus was, and he was welled up with the wonder of that was happening all throughout the Renaissance. What the fascinating thing is that medieval Christian thought adopted Aristotle's idea of a geocentric universe and embedded it into scripture. But here's the fascinating thing about that is that the philosophy grew around it to give the earth, to people on earth, a great sense of humility. So the center of the earth was the farthest place you could possibly be from heaven. Heaven being the celestial sphere where all the stars are, that was God's realm, that was heaven's realm. And so being at the center of the cosmos was as far away from the center as you could possibly be. And if we look at Dante's Inferno, we find that if you wish to go to hell, you go underground, deeper into the earth. And everybody knew the earth was round, so you get closer and closer and closer to the center of the earth, and that's where the devil is. And so we think even in Greek mythology, the river Styx goes into the earth, and Orpheus descends into the earth in order to get his Eurydice. So one of the ideas of the humanist was to say, no, we're not the worst place in the cosmos. We're better than that. So we're going to elevate the earth. And so Copernicus had the idea that he was going to elevate the earth out of its humble position at the center of the cosmos. Not its elevated position, but its humble position as the maximum distance possible from heaven, and place it, quote, closer towards the heaven by having it orbit the sun. So if the earth was orbiting the sun, it was closer to heaven, which gave greater prominence to humanity. And that was an essence of humanist thinking. It was a philosophical change in thought. And so a lot of people rebelled against it for that reason, that philosophical reason. Well, here's an important thing that occurred. His mathematical model wasn't really any better than Ptolemy's. And there was still the problem of the winds, of all the parallax that wasn't seen, all these things that Aristotle said that were arguments against the motion of the earth. Now Copernicus just simply said, hey, the mathematics works. I've gotten rid of the equants, but it's just as complicated as Ptolemy's, and it doesn't explain away Aristotle's arguments. This is a problem. So people weren't really thrilled with Copernicus's model, and people had problems with it when they advocated it. There's some significant social problems if you advocated his idea because it went against church doctrine, which followed Aristotle. In any event, so what it took was actual development of technology. But shortly after the 1540s, in 1572, there was a nobleman in Denmark by the name of Tycho Brahe, who looked up in the sky and saw a great star appear in the constellation of Cassiopeia. And that star was a supernova. And in 1572, that star made Tycho Brahe famous all across Europe. In 1574, he wrote about it. He wrote extensively about it. And it was his books and his writings about the supernova of 1572 were read all over Europe. And he became a superstar. He was kind of like the Einstein of the day because everybody knew him. Everybody knew about Tycho's star. Even when it was happening in 1572, they thought it was Tycho's star. So in 1574, he became world famous. And in 1576, as a result of him being world famous, he went on tour doing scientific things for his king. And in 1576, his king said, I want you to be a lord. I want you to be closer to court. I want to keep an eye on you because you're really famous. But because of your great accomplishments, I'm going to make you a lord. So he made him Lord of Ven, which was a little island off of Denmark. Now, Brahe wasn't really interested in doing that. He wanted to do science rather than be like a courtly person. So he said, look, here's what I want to do. I want to build an observatory on Ven. And the king said, well, of course, why don't you go to it? It'll be a great thing. In fact, make it the best. And in fact, that's what Tycho Brahe did. He wanted to make it a research institution for astronomy, which is exactly what he did. He built the first custom-built observatory in 1580. And it was called Uraniborg, inside a castle on that little island of Ven. So in 1577, during the course of the construction of the observatory, a great comet was seen in the sky, and that was attributed to Tycho Brahe. And Tycho Brahe was now regarded as one of the great observers the great astronomers of his day. In fact, his fame was so wide that his two kinsmen, Rosencrantz and Guildenstern, from Denmark, were featured highly in a play by a certain English playwright named Shakespeare in the play Hamlet. Go look it up. Yeah, by yond new northern star, Horatio. And the play is actually properly titled A Disaster, or Bad Star, the Bad Star of Hamlet. And so there's some mirroring between the story of Tycho Brahe and his inevitable fall in 1600 that actually Shakespeare wrote about. In any event, so in 1580, he built Uraniborg, which was a dedicated observatory that was based on his fame. And so what he did for the next 20 years was do incredibly detailed observations of Mars. Why did he do this? Well, he discovered that since the Almagest was written in 140 AD and monks were copying it and copying it and copying it, that transcriptions of these copies were getting errors. And so somebody had to finally go and actually update the thing by actually making new observations. So Tycho Brahe said, I'm going to do it. I'm going to be the guy. So he went out and did it. He made extraordinarily accurate observations, timings of the positions of Mars in the sky. And so he became an incredibly important person by his observations. He published his data, but by the end of the 1590s, he fell out of favor with his king and was exiled to Prague, and he had to get the heck out of there. So he was gone for various reasons, and he died in 1601. And when he died, his observatory was destroyed upon his death. But it wasn't too late. When in 1600 in Prague, he was met with by a young mystic named Johannes Kepler. And Johannes Kepler joined Tycho in Prague and worked with him and tried to wrestle the data that he'd gotten, that Tycho Brahe had taken before he died. And Johannes Kepler used that data. He worked very hard to get the data away from Brahe and away from Tycho Brahe's wife, who was his widow, and because Kepler was not a nobleman. So she didn't think that somebody who was not a nobleman should have that data. In any event, he eventually got the data. He eventually wrestled away because the local royalty saw fit to give it to him. And what happened was he looked at the data and analyzed it and tried all sorts of shapes with the data in order to see it. Can you make the orbits of the planets with circles? Do you need the epicycles? Do you need the deferents? Where can you put these things? He rejected Tycho Brahe's version of a geo-heliocentric model, where Tycho Brahe even made his own model out of his own data. And Kepler just said, nah, that can't work. And what happened is that Kepler tried all sorts of methods, and finally he gave up on the perfect circle. This perfection, this concept of perfection that was a thread from Aristotelian philosophy, that all celestial motion goes in perfect circles, that it always is perfect and it never changes and it's unchanging. This concept of perfection lasted for almost 2,000 years, and it was an infection in the mind, a meme, something that people couldn't get rid of, until Johannes Kepler just got so frustrated and just demanded to know exactly how the shapes were that he tried an ellipse. Instead of using circles, he tried an ellipse. So he said, wait, if I make the orbits not circular, but ellipses, guess what? And put the sun at the focus of one ellipse, then it works. I don't need equants. There is already a built-in equant. It's called the other focus of the ellipse. I don't need epicycles because the shape of the orbit is already taken into account. So Kepler determined in one fell swoop 2 laws in which he published in 1609. He published his first law of planetary motion, that all planets orbit in ellipses. And ellipses have a particular shape. They're not circles, they're more like ovals. So they have a particular shape. When they're nearest the sun, we call that perihelion. When they're farthest the sun, they call that aphelion. And the average distance between the sun and the planet along the ellipse, we call that the semi-major axis. So the semi-major axis is simply the average distance between the sun and the planet on there. Second of Kepler's laws that he published in 1609 was the area that as a planet orbits the sun, the line between the planet and the sun sweeps out an area. And so if we determine what the area is that is swept out by that line, say in a week's time or a month's time, but it'll always sweep out an equal area in an equal time, which means that when it's closer to the sun, it's moving faster, so it's sweeping along that orbit, so the triangle is wide and fat, but when it's far from the sun, it's actually a narrow and thin triangle. That's at aphelion, it's a narrow, long, thin triangle, but at perihelion, it is a fat, wide triangle. And so the appearance of the triangles might be different, but they have the same area. And so they sweep out equal areas in an equal time, which means that as it's at perihelion, it's going faster, and when it's at aphelion, it's going slower. Funny thing is, in 1609, after publishing this, Johannes Kepler learned about a young man named Galileo Galilei, and he sent a copy of his Astronomia Nova to him, and Galileo completely ignored it. Wonder what would have happened if he didn't. Anyway, so in 1619, Kepler further looked at the data and studied it extensively. He wasn't completely satisfied with the appearance of it. And he said, well, wait a second. If I look closely at this, I notice that how long does it take that things go slower the farther away from the sun they are. And he found that the time it takes for a planet to go around the sun is a very simple relationship to the average distance it has from the sun. So the period of the orbit in terms of Earth years squared is the same as the average of the distance between the planet and the sun cubed if that average distance is relative to Earth distances from the Earth to the sun. So now we've got this thing which is really fascinating. It's called the harmonic law, and it's sometimes just written p squared equals a cubed, where p is the period of the orbit around, and a is the semi-major axis of the orbit of the planet around the sun. So once again, the square of the time it takes the planet to go around the sun in units of Earth years is equal to the cube of the distance to the planet from the sun in Earth-sun distances. And those Earth-sun distances are called astronomical units. So the p squared equals AU, p squared equals a cubed, where p is in Earth years and a is in AUs. So of course that's 1 equals 1 for the Earth. And for Venus, it's the period, the A is about 0.72. And so I forget what that works out to be for the average distance is 0.72. So the average year is a few hundred days, is over 200 days. And for Mercury, it's about a third of an astronomical unit. And so it's about 88 days for its orbit around the sun. So what's fascinating is that this provides a relationship between all the distances. So if you can get, using Kepler's laws, because this is a law based on observations that Kepler did. Well, not Kepler, that Tycho Brahe did based on all the planets. So Tycho Brahe did accurate observations of all the planets. Kepler fit them with ellipses, found that the ellipses had specific semi-major axes, and found in 1619, published in 1619, his observation that the time it takes for a planet to go around the sun has a direct relationship to how far it is from the sun. So, and they're all referenced with respect to the distance between the Earth and the sun. So if we can just get that distance from AUs, so if we could just learn that, then we can get everything. Well, fascinatingly enough, the next guy to come along, we're going to talk next time we'll talk a bit more about the people who missed out on this. Galileo missed out on Kepler's work, but we can't really fault Galileo for that, because in 1609, when he sent it. Actually, Kepler in his later years went back and looked at his work, Astronomia Nova, and found that even he couldn't read it. So you can't really blame Galileo for not reading something that's basically impossible to read because of its complexity. But Kepler's laws were actually the beginning of what we call astrophysics, because he took actual observations and then created a theory surrounding them and did some sort of explanation on top of them. Now, this is really some fascinating stuff. And if we look at it, we say, well, wait a second, this is the beginnings of things. And so we're going to skip over to Italy in our next talk. And then after that, we'll skip across the waves over to England to see what Newton is going to do with it. But Kepler was on the verge of was one of the great stepping stones in astronomy. And if we look closely at what he did, when he passed, we actually look at some of his writings as he gets later in his life, we find that one of his most important works comes at the end. He was still a mystic to his very dying days. He really wanted to understand the mind of God. That was his goal with understanding these orbits. So when he wanted to understand that, he actually chose to say, well, what does this mean? And all his studies from the stars, when he looked up at them, his last writing was called The Dream, and the Somnium, the dream, where he actually looked up in the sky and said, I dreamed a dream that the stars were each of them surrounded by planets, just like our sun is surrounded by planets. And if it is surrounded by planets, then there are other places where other beings are looking down or up at us at a night sky. And each of those stars could have thousands of people or millions of people looking at us. And uncountable stars could be seen with the telescope that would have been invented during the latter part of his life. So really, Kepler kept his dream alive. And he thought in his last writing, which would be heretical even for that time to even talk about, was he dreamed of life on other planets or on other stars. Okay, so next time we'll talk more about the revolution that began science. See you soon.